continuing on with the example that we were doing in the last video, we had the revenue being the price times the number sold, or I may have written that the other way, the number sold times the price. We had figured out an equation, we had figured out our x-intercepts, and we used them to graph it. Now our x-intercepts, or in this case our n-intercepts, our horizontal intercepts, are -10 and +15. We know parabolas are symmetrical, which then means that halfway in between -10 and +15 will be the n value, the number of $50 increases in price that would maximize our revenue, that would give that maximum revenue. So to get that value for n, we want the midpoint or the halfway point between those zeros. So what we do is we take their average, we add them together and divide by 2, since we're adding two things together. When we do that, we get 5 divided by 2, which is 2.5. Now what that means, since we let n represent the number of $50 increases in price, the price, which is identified here, and I copied this down so that I had it, this expression here is my price. It's the $500 plus the 50 times n. So the new selling price that's going to produce that maximum revenue, the price, will equal the $500 plus 50 times the n. And our n that's going to produce the maximum revenue turns out to be that 2.5. It's the x-coordinate that produces that vertex. So if I've got 2.5 groups of 50, I've got $125 plus the $500. Originally, we're going to end up selling this for $625. So that selling price will maximize the revenue. The revenue then, revenue is equal to price times the number sold. So I can either go back to this entire equation, or I can use the fact that I already know what this equals, because I've just calculated it here, and just say, well, that's going to equal the 625 per canoe times 60 minus 4 times 2.5 canoes. Okay, so 60 times 60 times 4, try that again, 60, take away 4 times 2.5. There we go. I'm not doing all that much better here. So that's going to give us 600 and I wrote 52 there. Goodness. I think I still need a little more sleep here. 625 is multiplying the 50 that I get out of the 60 minus 4 times 2.5, and then we get an answer of 31,250. So that would be the revenue, the maximum revenue for that question. So I've just put a little final statement in here. I've squished it in the side here because I don't have enough room below. All right, what range of selling prices will provide a revenue greater than 30,000? So what we're really looking at is the fact that our parabola is an opening down parabola. We had figured out on the previous screen, or on the previous video, what we have here. This is our 15 as our n-intercept. This was our -10 over here. This is our revenue, and we had that maximum being 31,250. So if we want revenue to be greater than 3,000, we're really looking at, and I know I had figured out that y-intercept. Our y-intercept there was the $30,000. Oops. So our $30,000 line is right here. We've got a couple of options here. Okay, we could sub in $30,000 for our revenue and solve that equation for the values of n. That would give our $30,000. Or we can use the fact that we have a parabola and it's symmetrical. So we have a 2.5 that produced that maximum revenue. If I go 2.5 units this way and get that $30,000, this point here would also be 2.5 units away from that axis of symmetry, which will take us to a value of 5 here. So if we had a selling price of the $500, because n equals 0, so n equals 0 produces our revenue of $30,000, or n equals 5 produces a value of $30,000 for our revenue. We could then put our N values into the price equation, which are price expression, which is the 500 plus 50N, and find out those values. The other option is to actually sub the $30,000 into our revenue equation and then solve that. So I'm going to do both. Actually, I'm not going to do both methods. I'm going to do the one where I'm subbing this in. It just happens that the 30,000 was our y-intercept. If it doesn't work out that way, then we need to be able to solve it and know how to solve that. So I'm going to work through it the other way. Okay, so my revenue is going to be the $30,000. So I'm really replacing the R in the original equation with $30,000, and that's going to equal the 500 plus 50N times the 60 minus 4N. So just know that these are separate pieces here. Okay, so I'm going to have to expand and simplify that the right side of the equation so that we can actually work with the equation in its standard form. If I had 0 on the other side like I did up here, solving for the x-intercepts, then it's not such a big deal, but here we don't have that. So I'm expanding and simplifying here, and I hope I'm doing this correctly. And we're going to get a minus, and that should be 200N squared. All right, and then I'm going to bring everything to one side, subtract 30,000 from here, but then I'm subtracting it from both sides. That ends up going away, and we're left with a negative 200N squared. I'm going to put that first. Combining these, I have a plus 1,000N. And from here, I'm going to common factor a negative 200N out of both of those because that's common. That's going to leave me with an N, that's a bracket, N minus 5. And now I have factored form, so either N equals 0 or from this one N equals 5, which is exactly what I got here and here to produce that. Then my price I can calculate, I'll do that in a different color. My price would equal the 500 plus 50N, so 500 plus 50N. So 50 times 0 would just be 0. So the price could be $500. Or we go with price equals 500 plus 50 times 5, which will give us 750. So if we have our selling price anywhere between $500 and $750, that will give us the revenue that's greater than 30,000 because we're looking at all of this area of the parabola. So any value between here and here on the X, or in this case on the N, will produce that revenue to be above the 30,000 mark. All right, I'll put a little therefore statement and then we'll look at example 3. Okay, so I've just written a therefore statement down here. This next question is talking about an orchard. If 100 pear trees are planted, then the annual revenue is $90 for every tree. So my revenue would be 100 times the 90 because it's $90 for every tree and there's 100 trees. If more trees are planted, they have less room to grow and generate fewer pears per tree. As a result, the annual revenue per tree is reduced by, so the revenue is reduced by per tree. So the amount of money you're making per tree is no longer the $90. It's going to be decreased by groups of 70 cents for every additional tree planted. No matter how many trees are planted, the cost of maintaining each tree is $7.40 per year. So we're going to calculate or create a revenue function, a cost function, and then we're going to get a profit function, which is your revenue minus your cost. So we'll do that on our next page here. Okay, so we've got our revenue being the number of trees times the amount you get per tree. We're starting with 100 trees, and we're getting initially $90 for every tree. But we know for every extra tree we plant, so if we add 1x to the, back that up, I'm on the wrong one. A number of trees is over here. So if I increase the 100 by groups of x for every 1x that I'm adding to the orchard, every extra tree, I'm now going to decrease the amount I'm earning per tree by groups of 70 cents. So I'm going to take off 0.7 per every extra tree that I'm planting. So in this case, X represents the number of extra trees that are being planted. Okay, as far as a cost function goes, we know that the cost of maintaining each tree is $7.40 every year. So we've got $7.40 or 7.4, I don't have to put the zero there, times the number of trees. Now, because these two pieces are related, our number of trees are represented up here by the expression 100 plus x, because we don't know exactly how many trees we're going to have. We know we're starting with 100, but then we're going to actually increase that by x extra trees. So whatever that is will be times by $7.40. Now, how many pear trees should be planted to maximize the profit from the orchard for 1 year? So our profit equation is always equal to the revenue, the money you bring in, minus the costs. So what we have here is our revenue function, 100 plus x, multiplied by the 90 minus 0.7x, and that's going to be decreased by 7.4 times 100 plus x. Now, I can't get the maximum when it's written in this form. What I would do with this is expand and simplify it, and then work on getting the vertex of that. All right, so take a moment or two, expand, simplify, see what you get. Okay, if you expand and simplify, you should get the equation that I have right here as your final profit equation. Now what I've done here, and there's different ways to do this, but I chose to find the x-intercepts, which make the profit equal 0. And now what I'm going to do is find the midpoint. So these are the zeros, the midpoint, add those together and divide by 2. Will give you the value of x that will produce, so that's divide by, whoops, undo, wrong spot. Okay, we want this divided by 2, which would be 18 divided by 2, which is 9. So if we plant 9 extra trees, that will maximize our profit. So how many pear trees should be planted to maximize the profit? 109 trees, because the number of trees is this 100 plus x expression. So 100 plus x is 109 trees to maximize our profit. Now there's a couple other things I want to point out here. We could have completed the square to put this in vertex form, so that's an option. Another option, what I'd like you to do is try this calculation. If you take the negative b, which is this negative 12.6, and divide by the 2a, which is negative 1.4. So if we go with the negative b, which is 12.6, and divide by 2a, which is negative 1.4, do that on your calculator, see what you get. Okay, you should have gotten 9. The quick way to get the independent variable that produces the maximum when you have an equation in standard form is to take your negative b and divide by 2a. And that will give you the x value that produces the maximum value for the function. It gives you the x coordinate of the vertex. So that's a quick thing to know, and it would save us oodles of time when it comes to solving for that when we have standard form. So that would be something important that I would add to your summary sheet for this unit. All right, the last question here is what range of number of pear trees will provide a profit greater than 9,000? I'm going to do a solution on the next slide to that. I want you to try that now that we've done a bunch of questions, and then you can just check your solution.